Good morning, everyone. I'm Andy Hoell of the NOAA Physical Sciences Laboratory, and with my colleague Hailan Wang of the NOAA Climate Prediction Center, we will overview challenges, gaps, needs, and opportunities of flash drought prediction. In the first half of the presentation, I will discuss challenges and gaps. In the second half of the presentation, Hailan will discuss needs and opportunities. We use three themes to describe challenges, gaps, and needs of flash drought prediction. The three themes are operational forecasts, the tools or initialized prediction systems used to make operational forecasts, and prediction skill and predictability of environmental conditions related to flash drought. For operational forecasts, we note that flash drought forecasts are in their infancy, and this forces stakeholders to use operational forecasts that were not specifically designed for flash drought, and that existing operational drought outlooks are not consistently skillful. The Climate Prediction Center's monthly drought outlook is the operational forecast product that best applies to flash drought. The monthly drought outlook is released once each month and predicts drought development over the subsequent 4 weeks. The monthly drought outlook was created in response to the central United States flash drought of 2012 and went into operation in the summer of 2013. The monthly drought outlook failed to forecast the 2017 Northern Great Plains flash drought. We illustrate this point using the latest U.S. Drought Monitor release in May, June, and July of 2017, and the monthly drought outlook valid at those times. The monthly drought outlooks in May and June of 2017 did not forecast drought development that was observed over Montana, North Dakota, and South Dakota. More generally, when accounting for the performance of the monthly drought outlook during 2013 to 2019, we find that it was not consistently skillful. This is illustrated using the time series of monthly drought outlook verification provided by the Climate Prediction Center. Skill is defined as the difference between the fraction of correct forecasts of drought improvement, removal, persistence, and development using the U.S. Drought Monitor as truth, and a persistence forecast baseline. Skill is computed for the entire United States. The maximum possible score is 100, and the minimum possible score is -100. As the time series indicates, the skill of the monthly drought outlook is variable. The highest skill forecasts were issued in 2017, but in recent years, there have been many low skill forecasts. We now turn our attention to forecast tools. Many prediction systems used today are inadequate for guiding skillful and detailed flash drought forecasts for two reasons. First, they are infrequent, untimely, and their resolutions may be too coarse. And second, they lack the breadth of variables relevant to flash drought. We used the Northern Great Plains flash drought in 2017 to illustrate the limitations of flash drought forecast tools. The left-hand portion of the slide describes the rapid onset of the drought at Glasgow in northeastern Montana in May, June, and July of 2017. Soil moisture percentiles from the UCLA Surface Water Monitor, shown in the top row, indicates a standardized soil moisture decline from the 70th percentile to the 10th percentile between mid-May and mid-June. The rapid land surface drying was related to the failure of precipitation from mid-May to mid-July, on average the wettest time of year in Glasgow, and above average temperatures. The right-hand panel shows the cumulative precipitation anomaly from May to July 2017 at Glasgow and observations, as indicated by the black line, and for sequences of global forecast system predictions at various lead times, the red and blue lines. Reconstructing a forecast based on various lead times allows one to assess how far in advance an observed outcome could have been predicted. Comparing the forecast precipitation accumulation with the observed precipitation accumulation in Glasgow, we find that sequences of longer than 3-day lead predictions did not capture the evolution of precipitation anomalies during the spring and summer of 2017. This result, along with predictions from the North American Multi-Model Ensemble made in advance of the season, strongly suggests that this drought was unpredictable in the generation of models available in 2017. The forecasting community has more tools than ever before. But despite consistent improvements to established efforts like the North American Multi-Model Ensemble, in the emergence of new programs like the Subseasonal Experiment, also known as SubX, the tools remain inadequate for flash drought prediction. We use Table 1 from the publication Describing SubX by Pigeon and colleagues to illustrate this point. At the time of publication in 2019, SubX was comprised of 7 models, all of which follow different protocols. Predictions were made available for each model on different days of the week, and the forecast ensemble size for each model was different. Moreover, all forecast data was available at common horizontal resolutions, which may be too coarse for flash drought predictions. Finally, we turn our attention to prediction skill and predictability. Currently, there are only a few known sources of predictability. These sources include Rossby waves in the atmosphere that originate from distant locations, and the initial state of the land surface. Also, models are imperfect and many lack skill, and the multifaceted nature of flash drought requires that many variables, and not just a single variable, be forecast accurately. In a perfect world, every drought has a systematic cause that can be predicted, but in reality, we know of just a few systematic causes, and we have found that only a few models can predict them. Also, the same source of predictability may not apply to each and every drought, so we are constantly searching for new sources of predictability that we may be able to leverage for the skillful prediction of future flash droughts. In the case of the 2012 Central United States flash drought, DeAngelis, Wang, and colleagues found that the origins of the drought could be linked to atmospheric waves, called Rossby waves, originating over Asia. But they also found that few models participating in SubX could forecast this phenomenon. With regard to the 2017 Northern Great Plains flash drought, its predictability sources, if any, remain unknown. My colleague Hailan Wang will now present on the needs and opportunities of flash drought prediction.
This is Hailan Wang from NOAA Climate Prediction Center. We will next discuss the needs and opportunities of flash drought prediction. We will use the same 3 themes as those for challenges and gaps: operational forecasts, forecast tools, and prediction skill and predictability. For operational forecasts, the indices for flash drought are preferably integrative, in order to characterize flash drought as a multivariate and multifaceted phenomena. The indices should use the same as those in the monitoring community for consistency. The flash drought forecast should be probabilistic in order to incorporate the effect of the chaotic nature of the Earth system, particularly that of the atmosphere. The probability information of flash drought forecast is also essential for addressing user needs and facilitating their decision-making. The forecasts need to be issued frequently, ranging from daily to weekly, in order to capture flash drought as a rapid evolving phenomena. The flash drought forecasts need to be aligned with impacts when possible. Examples of these impacts include those on agriculture, such as soil moisture, evapotranspiration, and vegetation health. NOAA CBC is an operational center to produce and issue forecast products for the public. Currently, it is one of the key tasks at CBC to develop and produce flash drought forecast products. A main goal is to develop experimental probabilistic flash drought forecasts. This work includes the development of flash drought prediction system comprised of dynamical and statistical components. It currently is in its infancy and will take years of research and development to materialize. A flash drought-related product that CBC plans to release next year is an updated U.S. Week 2 Hazards Outlook, in which the Week 2 flash drought forecast will be added. The U.S. Week 2 Hazards Outlook is released every weekday and targets a Week 2 forecast period. It currently includes precipitation, temperature, snow, and wind. The product uses a probabilistic and categorical format. They're produced by subjectively integrating objective inputs, one of which are dynamical model forecast ensembles. CBC is currently working on adding Week 2 flash drought forecast to the map and expects to release a new product next year. Finalizing this new operational product has several requirements. They include discussions with both CBC Drought Outlook and U.S. Hazards Outlook forecasters, coordination with the NWS Regional Operational Center staff, climate service program managers from that region, and when and where available, contacts from CBC's core, deep relationship partners, such as USDA. Next, we turn our attention to forecast tools. As Andy has pointed out, many of the current prediction systems are inadequate for guiding skillful and detailed flash drought forecasts. The forecasts they produce are infrequent, untimely, of coarse resolution, and lack the variables that are necessary to produce flash drought forecasts. Therefore, dynamical model forecasts need to use improved protocols. Our recommendations include consistent initialization dates, more frequent forecasts, higher spatial resolution, make more variables available in the forecast output, produce more ensemble members. The production of multi-model based operational forecasts also requires statistical post-processing to improve the scale and probability of the dynamical forecast. This includes bias correction, calibration, and consolidation. Further, multiple land surface models are required to produce high-resolution hydrological forecasts. These land surface models will be forced with the bias-corrected and calibrated meteorological forecasts. In addition, statistical prediction models should also be considered. They can potentially add scale for regions and seasons that dynamical models show little prediction skill for flash drought. They can also help assess flash drought predictability. Finally, we turn our attention to prediction skill and predictability. Exploratory research is required to identify new sources of flash drought predictability. For those identified predictability sources, research is required to assess how well these sources and their effect on flash drought involvement are represented in current and future generations of forecast models. The investigation can also help diagnose sources of model biases related to flash drought processes and inform model development. In addition, climate has been changing. It is necessary to perform research to better understand the effect of climate variability and change on flash drought prediction. Considering the data and tools that are used to produce flash drought forecasts, the dynamical models and forecast systems need to be further improved by reducing model biases and developing more advanced forecast strategies. Flash drought forecasts should also leverage advancements made in monitoring, particularly for early warning indicators such as changes in evapotranspiration. Lastly, flash drought prediction should incorporate developments in statistical models by, for example, taking advantage of recent advancement in machine learning approaches. These statistical models can potentially complement dynamical models and add skills for regions and seasons that dynamical forecasts are of limited value. This ends our presentation on flash drought prediction. Thanks for listening.